Thank you, Tom, and good morning, everybody. I'm going to share my screen here. I have some slides. Hopefully you can all see that. And again, thank you for inviting me. I'm Josh Hamilton. Before I was an administrator in higher ed, I was actually a professor at Dartmouth Medical School for most of my career. I'm trained as a toxicologist and pharmacologist, and so toxicologists look at the adverse effects of chemicals on human health, and pharmacologists look at the beneficial effects of chemicals on human health. And they're two sides of the same coin. And I taught their undergraduates, graduates, and medical students, and also ran a research lab for the entirety that I was at Dartmouth Medical School, with about 15 people in my lab, focusing mostly on cancer research, both the causes of cancer from environmental agents and interventions, medical interventions to help ameliorate or potentially cure cancer, and also worked on cystic fibrosis for many years. So what I'd like to talk to you today about is our trust in science and what we know and how we know it. And this will be in the context of COVID. I'm not an infectious disease expert. And so we're not going to get into the gory details of COVID, but I think I've been certainly following it as you all have. And I think there's a lot in respect to COVID that's worth talking about in terms of the science and how our information about it is evolving, and just what that process really looks like. So first, since I'm a toxicologist, I'll use this as an example. There are a lot of health risks out there in the world, and some of them are obvious to us. So on the far left is acid mine drainage from a former copper mine. This happens to be in Vermont, a copper mine that I worked on with the town and with the Environmental Protection Agency. And you can see the obvious pollution there, and it's impacting the river below it. In the middle is a typical urban environment. This is Shanghai, China. And you can visibly see the heavy air pollution. If you were closer, you'd be able to see land and water pollution. So again, that's pretty obvious to us. On the right is actually the site of the World Trade Center bombing. So when those planes crashed into the Twin Towers, they not only obviously took enormous human life, but those towers burned and fell, and they created the largest toxic waste site in New England when they did so. And the smoke that you can see from those burning towers greatly impacted human health, particularly first responders, but many other people in the greater New York area. There's also things out there that we can't see. We can't see them or smell them or taste them or feel them, but they're out there. So here's some examples that are things that I had worked on in the past. On the left is electromagnetic fields from high power lines. We don't know much about it. Does this impact human health or not? And they're hard to measure. You don't feel them, you can't see them. And so this is something that people worried about for a long time. On the right, you can visibly see mercury there, but the mercury we worry about, you can't see. It's the mercury that might be in fish or shellfish or other foods that gets into our food supply from the environment, principally by burning coal. And again, for many years, we didn't know it existed. We couldn't see or taste or smell it, but it would build up in our bodies and cause human health effects. So these are just some examples of things we can't see. There's a matrix of knowledge that I wanted to talk about in terms of science. Now, many of you may know that Donald Rumsfeld was famously quoted as going through this list. He didn't invent this, by the way. This matrix has been around for a long, long time. And he got a lot of grief for it, actually, but it's actually a very standard way of thinking about the world, not just science, but the world. There are known knowns. There are things that we are aware of and that we understand. And we often, facts are an example of known knowns. We know that 2 + 2 = 4. And so there are many, many things that we have discovered about the world, and we know about them and we understand them. But there are also known unknowns. There are things that we're aware of, but we don't understand. And COVID is a good example of that. If you think back to almost exactly a year ago, when COVID emerged as an infectious disease, we knew nothing about it, but we knew it existed. We knew it was an emerging problem. And so that's a known unknown. There are unknown knowns, things we aren't aware of, but that we do understand. We don't know whether it'll snow a year from now. But when it does, we'll understand it because we know a lot about the weather, and we can predict the weather and we can measure the weather when it actually happens. And then there's unknown unknowns, things that we aren't aware of and we don't understand. The bottom of the ocean, for example, we know almost nothing about. We don't know what's there and we don't understand it, but we'd like to. And so that leads to exploration. The way scientists do this is through the scientific method. So starting at the top, they make an observation. Maybe they see a new disease emerging like COVID, and then they go through this process in this clockwise way. They identify the problem, they research it, they may then develop a hypothesis for what they think is going on. They design an experiment to test that. They do the experiment, then collect and analyze the results, and then try to draw a conclusion from that. It's shown in a circle here because this basically never ends. It's rare, almost never happens that we do something once and we totally understand it and never have to study it again. What's more typical is we start to study something and it often provides the answers, but it often leads to more questions than answers. And so that leads to new observations, new hypotheses, and new discovery. And this is called the empirical basis of science, that we build on prior knowledge and we continue to poke and poke and poke at things to try to understand them. So one of my favorite scientists is the late Richard Feynman. You can see him on the right there. Just considered one of the most brilliant minds of the 20th century. He was a physicist who made very important discoveries, but also just a great teacher, and really enjoyed talking about science to the general public. I was actually fortunate enough to hear him lecture when I was a graduate student at Cornell, and I was in a very large auditorium. He was giving a physics lecture, and 2/3 of the people in that auditorium were not taking that class. They showed up just to listen to him lecture. People who weren't even science majors just enjoyed listening to him explain science so well that they showed up. Carl Sagan, by the way, was at Cornell at the same time, and
Wow.
likewise, packed audiences every time he lectured. People just wanted to hear him explain how science worked and how the world worked. Another great astrophysicist. So anyway, Richard Feynman had many really wonderful quotes over the years, but here's two of my favorites, and they speak to scientific objectivity and also to the empirical nature of science. So the first one says, "It doesn't matter how beautiful your theory is, doesn't matter how smart you are, if it doesn't agree with the experiment, it's wrong." And this is really important. When I was a young professor, we had an outside speaker come in once and talk to my students. And he said, you know, to me, science is that you form a great hypothesis, you fall in love with it, and you spend the rest of your life trying to prove that it's right. And so I had to talk to my students after that lecture, because I said to them, I think that's completely backwards and wrong. That is not science. In fact, you should never fall in love with your hypothesis. And you certainly shouldn't spend your life trying to prove it's right. The only purpose of a hypothesis is to design a good experiment. And the best experiments actually are designed to try to disprove the hypothesis, not prove that it's true. But you certainly shouldn't fall in love with it. What you need to do is actually look at the data and the results themselves. They are what they are. And if the model that you proposed doesn't fit the data, then your model's wrong, and you need to come up with a new model to explain the objective data that you gathered. And this is really important. And it's hard because scientists are human beings, and we do tend to fall in love with our own hypotheses, but we have to continually be as objective as possible. His second quote is really important too. He says, "Scientific knowledge is a body of statements of varying degrees of certainty, some most unsure, some nearly sure, but none absolutely certain." And this is another pinnacle of science, is a good scientist will never say anything with absolute certainty. We will say it with a high degree of certainty, but not absolute certainty, because we learn new things all the time and things get adjusted over time. If you think of what we did in medicine 50 years ago and how we thought the human body worked and what we know now, it's evolved enormously. And that's because we were willing to gather new data and adjust our understanding of the world. So there's also a kind of a hierarchy of scientific disciplines to understand here. So mathematics is considered the purest science, and it's the most advanced. It's not done. There's more math to do for sure, but it's a very mature discipline. Simple math, algebra, trigonometry, calculus, these are well-established components of math that have stood the test of time, and we use them every day. And if we were ever to encounter an alien species from another planet, we probably would have a hard time communicating with them verbally, but we would probably start the conversation with math, because almost certainly if they were as advanced as we are to be able to meet up with them, they would have discovered the same mathematics that we did. And that's because the math itself is pure. 2 plus 2 will always equal 4. And they might express it differently, but the fundamental math is the same. Physics can be considered essentially applied mathematics. It's a way of describing the physical universe, and that's typically done using math to describe that, whether we're talking about gravity or acceleration or friction or how the planets move. That's often done in mathematical terms. Chemistry and engineering are essentially applied physics. And so chemistry relies on physics to understand how atoms and molecules behave and how they interact with each other, and that leads to chemistry. And likewise, engineering uses physics every day to understand the loads on buildings and how to build an airplane and so on. Biology then is essentially applied chemistry. Our bodies are giant chemical factories, and that's why we exist. And so understanding biology means you have to understand chemistry. And finally, medicine is essentially a subdiscipline of applied biology, understanding the human body and developing medical procedures or approaches to either retain health or restore health in some way. As you go down this list, though, we have less and less certainty. So as I said, we know a lot about mathematics. It's very mature. Physics less so, but again, very, very mature. There's a lot of chemistry we still don't know. There's even more biology that we don't know. And for sure, medicine is a very young discipline, and we have a lot to learn about the human body and how it works. So here's an example of something we know with high degree of confidence. As Orphan Annie would say, the sun will come out tomorrow, bet your bottom dollar. We have pretty high certainty that tomorrow morning, in quotes, the sun will rise. Now we know it actually doesn't rise. We perceive it as rising because we also know that the Earth rotates on its axis, and that's what creates the sunrise and sunset. We know with great precision how the Earth moves around the sun and how the moon moves around the Earth. And so we can also predict the tides, for example, on Earth with great precision. We know exactly when high tide will be in Portland tomorrow, and we can predict when it'll be 100 years from now with pretty high degree of certainty. Here's something we don't know much about. Again, the coronavirus. A year ago, we knew nothing about it. We have learned a great deal, and we continue to learn a great deal, but this is something that we don't have a great degree of certainty on, but we're rapidly learning about every day. So there's an interesting field of behavioral psychology that focuses on perceptions of risk, and this gets into this idea of what we know and what we don't know. So this is an interesting chart. Let me walk you through it. So this vertical axis where it says unknown at the top, this is a scale where at the bottom, we know a great deal about something, and at the top, we know almost nothing. And going from left to right, that other axis is the dread axis. So on the left, we don't dread anything at all. And on the far right, we have a great deal of dread about it. And the dots represent various human enterprises and are basically surveys of people of how much they know about it and how much they dread it. And the size of and color of the dot dictates how much people want us to regulate it. So where do you think nuclear power is on this chart? It's way in the upper right. People don't know much about it, and they're really afraid of it, and they want us to regulate it. Lawnmowers are in the lower left. People feel like they understand what a lawnmower is, they know how it works, they're not really afraid of them. Probably should be. They're pretty dangerous, actually, but they're not. They're not afraid of them, and they feel like they understand them. And so this gives us a real sense of not just our own knowledge, but how we react to that knowledge. I would probably put the COVID virus up in this upper right quadrant. We don't know much about it collectively as a society, and we're pretty afraid of it right now. And because of that, we want to regulate it and manage it. So, thinking of this coronavirus and how it's evolved, our understanding of it has evolved over time has been a fascinating sort of compressed way of thinking about how the scientific process works and how society grapples with something that it doesn't know. So how many unique viruses are there? Where did this come from? Well, it's estimated that there are about 2 million unique viruses that are collectively hosted by mammals and birds on Earth. Now, viruses essentially can't exist on their own. They exist by having a host and then replicating and moving to another host. And there's a lot of debate about whether viruses are alive or not. They're particles. They don't breathe. They don't really metabolize, but they replicate like crazy. And so it's a very interesting debate in biology about whether viruses are considered alive or not. But they certainly exist, and they create great havoc at times with human health and other animals. Worldwide, it's been estimated there may be as many unique viruses on Earth as there are stars in the universe. And that estimate is 10 to the 31st power, which means you'd add 31 zeros after that number, a really ginormous number, one that we can't really even wrap our heads around. But if you think of all the viruses for animals, for plants, for bacteria, for others, it's certainly just an enormous number to think about. And we're talking about not the number of them per se, but the unique number of them, how many unique kinds of viruses there are. Many of these viruses can cross between species, which is how COVID emerged. I happened to work on the so-called swine flu. So here's an example of this. You may remember in 2009, there was this outbreak of what they called swine flu. And there's a picture of a pig here on the Environmental Health Perspectives Journal, which came out around that time. And this actually is a form of the influenza virus known as H1N1. So it's actually a very common virus. It was not a new virus when it emerged. And in fact, my lab and others have been studying it for many years because it's one of the few strains of influenza that not only cross between mice and humans, but where mice essentially get the same form of the flu that humans do. So if you want to study the flu, using H1N1 in mice is a model where you can study what it does to the body and know that it's essentially the same virus and the same outcome as you might see in a human being who gets the flu. So this is just an example of cross species. What happened in 2009 is that a variant infected pigs and then reinfected back to humans. And that created the outbreak, which fortunately did not turn into a pandemic the way coronavirus did, but it's just another recent example of this. And this happens regularly, and we expect it to happen even more frequently in the future. So let me just say a couple words about epidemiology too, because this is the major tool in science that we've been using to study COVID. So epidemiology is the scientific study of the distribution of diseases and other health measures in specific populations. So this is always done at the population level rather than the individual level. Infectious disease epidemiology is a subdiscipline of epidemiology writ large. And so this tracks the sources, spread, outcome of infectious agents. So there's 5 W's in epidemiology, which are common to science and journalism, as it turns out. What, who, when, where, and why or how. So what's going on, who's being infected, when and where is this happening, and why and how is this spreading? And those are the basic tools that we've been using for the last 12 months. One of the people that's considered the father of modern epidemiology is this fellow here, Dr. John Snow. So he was tracking cholera outbreaks in London, and he tracked them to specific wells in London that were used for drinking water. Here's an example here. In 1854, there was a cholera outbreak And you can see the map of the outbreak there. All those little dots on that map are individual cases that he tracked going house to house. And what he learned was everybody who got sick from cholera in that neighborhood drank water, and those that didn't get sick never drank water, they only drank beer. So I guess that's a good plug for drinking beer if you live in a world of cholera. And a lot of people did that. There were men in particular who would get up and drink beer in the morning, beer at lunch, beer at night, and not ever drink a glass of water. But by doing this investigation, he realized that there was a well that they all shared, which had cholera in it, and he was able to track that outbreak. And this is fundamentally what we still do in epidemiology today. So what did we learn about the coronavirus and how did we learn it? Well, as you know, the first outbreak was in China, and it immediately suggested a novel virus that could potentially cross over to humans, and in this case from a wild animal species. And we learned it could be transmitted rapidly and could lead to illness and death. And this was just about a year ago. It was quickly identified as a member of the coronavirus family. And so the initial concern was about contact transmission. That is, touching a surface with your hand and then touching your face, for example, because the coronaviruses include those that cause the common cold. And that was the best form of transmission of the cold viruses is typically through surface transmission, as opposed to, say, breathing. And so you could transmit it by sneezing on somebody or coughing, but typically they worried about contact transmission. But what we rapidly learned is a couple of things. First, the aerosol transmission for this virus was very important. And over time, we learned that in fact, surface transmission was much, much less important for this particular virus. So mask, social distancing, hand washing were recommended to try to prevent the spread. The genome, while this was going on, so its DNA sequence was rapidly determined. And based on that, we started to develop vaccines, which are now with us. And this is in and of itself an amazing story. It's a brand new technology for how these vaccines were developed. And it's a way in the future to rapidly respond to infectious agents like this. Eventually, the epidemiology indicated that aerosol transmission was the principal method of transmission, reinforcing the idea of masks and social distancing. But we also learned with this virus that it's highly variable, both in its transmission, the demographics. So for example, young people respond in general very differently than older people. And the severity of illness varies from people who are completely asymptomatic to those who end up in the hospital and in ICU and potentially dying from it, and everything in between. And more recently, as you may know, we've identified some mutant forms that are arising, which are of new concern. So turning to the vaccines, this is another branch of science, and there's a very clear process for how these are developed. It starts always with preclinical investigations. In this case, inventing the vaccine itself from the genetic sequence of the virus, testing it in animals and other preclinical models, so we understand its safety and its stability and other factors. And then if that all goes well, you propose and get approved for a phase 1 trial. And this is a fairly limited trial, and these first tests are primarily focused on the safety and dosing of, in this case, the vaccine. And making sure that it doesn't cause immediate harm, but also what dose is tolerated and whether there's any obvious side effects to it. Based on the success of that, one goes to a phase 2 trial. This tests a much larger and more diverse group of people. And here you're starting to look at efficacy. That is, does it work? And so they're looking for an immune response to the vaccine in this case. In phase 2s, you sometimes, or typically either give the vaccine itself or a placebo, meaning you give somebody an injection that has nothing in it just to see if there's a difference. Or if there's a currently available formulation, say another vaccine, you would say, well, is it better or worse than this other vaccine? So you'd compare them head to head. And then depending on how that goes, you can move to a phase 3 trial, which is a much larger, very extensive examination of large cohorts of people. And here you're also looking at young and old, and a much larger cross-section of society to determine its efficacy. Oops, sorry. And finally, phase 4. Phase 4 actually comes after approval. And phase 4 for drugs or vaccines is where you continue to gather data on its efficacy and safety, particularly whether there's any side effects you didn't discover during the early phases of the trials, but with the whole population at large, you might see over time. And so we never really stopped gathering data on these things. So when you have something like a vaccine or other approaches to mitigate COVID, there's this general chart that people pay attention to on cost versus benefit. So on the left, we're looking at the decrease in risk as we go from top to bottom. And that blue dotted line shows you how if you continue to invest resources, which is down at the bottom there, the increased cost of risk reduction, the risks go down and down and down. And eventually they go down to some point that you've defined as being optimal. On the right-hand side is the benefit increase as you do that. And that's the black line that's a kind of a bell curve. So as you invest and as you reduce risks, you're gaining benefits to society. But there's a crossover point where you can continue to spend more resources and you don't really get any more risk reduction or increased benefit to society. Now, finding that inflection point is a matter of great debate. It's not obvious where that point is, but we know from studying prior circumstances that there is such a point, and there's a point of diminishing returns where even if you do more and more and more, you don't really have further reduction of risk and you don't have further tangible benefit to society. And as that curve shows, in most cases, the benefits can go down to society. So for example, with COVID, if all of us were told to stay in our houses and never leave our houses and all businesses were shut down and nobody could go to work, there would be a cost to society of that, right? And so what we're doing now, we're all of us, the state of Maine, the United States, is weighing these trade-offs. How much should we restrict people to reduce the risk of the disease? And what is the societal impact of that when we do that? And this is more policy than science, but just wanted to mention that there's no perfect solution to this question, but it's something that we need to think about all the time. So as you think about something like COVID as just a person in the population and wondering, well, how do I know what's right or wrong? How do I understand this? I would recommend that you go first to really good sources of information that are well trusted. So these would be things like the US Centers for Disease Control and Prevention, the National Institutes of Health, which is where Anthony Fauci works, the National Science Foundation, the World Health Organization, and so on. These are well-established scientific organizations that study these things carefully and make recommendations to society based on those. Down at the bottom, one can also look at peer-reviewed individual scientific publications. The challenge there is you can look at an individual paper and taken out of context, you have to be careful how many conclusions you draw from one study. Science really relies on many, many studies, and it's the sum total of all of that knowledge where we get our best recommendations rather than individual studies, which aren't necessarily wrong, but may just present a very small piece of the total picture. And you can also look at textbooks and reference books and technical encyclopedias. The problem is these typically were published, 1, 2, 10 years ago, and so they may be a little bit out of date for something new like COVID. If you do look at individual studies, and the media reports on these all the time, you'll read headlines that say, new study comes out and says ABC. You have to be very careful of that. Were they reputable scientists at a reputable institution that did the study? Was it a peer-reviewed grant that funded it? Because that means other scientists looked at the experimental design before deciding to spend the money to do the work. Do the authors cite their data separately from their own conclusions? Because the data is one thing and their interpretation of it is something else. And do they cite caveats or limitations to their study? Do they tell you what the deficiencies are in their study? Are they cautious about extending the interpretation broadly beyond the limit of the study itself? And are they not citing the data out of context? I would say be very, very suspicious of other reports that don't follow these guidelines, particularly anything you read on the internet, where literally, if you can come up with an idea, somebody is promoting it as a theory and can tell you things that they claim will support it. But that's the Wild West, really. So doing broad internet searches, one has to be very, very careful when you're trying to find objective information. So I will stop there and I'll stop sharing my screen. That was my presentation, and thank you for listening to me. And I'm happy to talk about that or anything related to that you'd like to chat about.